Not hundreds of thousands, but he dumped all this like money he'd inherited. He dumped it into Apple stock the day Steve Jobs announced the Intel. It was literally the best stock market advice I've ever given any human being in all of history. Apple can just wake up on a Tuesday morning, look at all the data and say, we're going to turn down the chip space we're going to give for crypto, and we're going to turn up the chip space we're going to do for video editing. And that'll be called the M2.3 or whatever. And because of portable operating systems and the ability to recompile, they can just play that.
Hey everyone, David Bombal back with Dr. Chuck. Dr. Chuck, welcome.
It's good to be back. I really enjoyed our last interview, and I watch it and I promote it all over the place because it was a lot of fun.
Really great to have you back. So before we get into details, give us an update. What have you been up to? Because last time you were talking about a whole bunch of things that you were working on.
The thing we talked about last time was what I call the path to the master programmer, which is taking kind of a skilled trades approach to teaching programming and focusing not on the theory of programming or the math behind programming, which I still think is a fascinating topic. I just don't think it's what should be front of mind for most people just starting out, any more than queuing theory should be the first thing that a CCNA person starts talking. There's math behind networks, but that doesn't mean your job is about the math behind networks. And so I told you last time that this is a long process for me. It's going to be a couple of years before I finish all this stuff. And so what I do is I tend to have a set of courses, and I've got 4 out there on Coursera right now, and I'm working on my 5th, and it's going to take me 2 years to make my 5th. But this course is turning out to be lovely. First 4 courses are Python, Django, PHP, and Postgres. Those are kind of like just learning to program a little bit. And then C is my next course. And then hardware, architecture, and Java will be my capstone when it's all said and done. And Java will overlap with internships, right? So the first half of Java is like, what's the language? And the second half is like, let's go to work. Because I really am just getting stronger and stronger with the notion that the only way you really learn to program is to work and not just do synthetic things. And so, it's like, I got to stop just teaching you syntax at some point and put you to work, get you in a job and hopefully pay you. And so I've been working on this C programming for everybody, www.cc4e.com. And the crown jewel of C for everybody is this textbook. C programming, just touching this textbook makes the hair on the back of my neck stand up in a good way. This is beloved. Millions and millions and millions of software developers cut their teeth on this textbook. Brian Kernighan, Dennis Ritchie. But there are 2 editions of the textbook. The textbook has a 1978 edition and a 1984 edition. In 1978, Kernighan and Ritchie were not sure if Unix was going to be a good idea. They were not sure if C was going to be a good idea. They knew they liked it. They were in a research lab at AT&T, and they were using it, and they loved it. And this book is kind of like, look what we have found. Look at this really cool, weird thing you've never heard about. And so the tone of the book is a tone of like, hey, we're still researching this. But this is what we like about this stuff. And this is what's cool. And this is what, you see that this and the whole word thing versus character thing. And they're kind of always like breaking the fourth wall and apologizing to the reader or explaining to the reader or giving more detail to the reader. And so this 78 book, changed the world. And we can talk a lot about how I see the world as like previous to 1978 and post 1978. And 78 is like everything changed in 1978. And I could go on for hours about all the things that I think the modern era of computing started in 1978. And I'm not talking like networking. I'm talking about programming and hardware and the ability to make our modern M1 processor. In 1978, the foundation was laid that made it so Apple could switch from Intel to M1, literally, period. The M1 processor potentially wouldn't even exist if it weren't for the C language, Unix, and what they did back then. But here's the thing. I want to give this course not just as like, I'm going to teach how to program C. I mean, there's like 18 million courses that teach you how to program C, and I think they're mostly pretty bad because they mostly take a language that should really never be used by 98% of the programmers, and they teach it as the first programming language. This programming language is ugly, and it's bumpy, and it's flawed, and it breaks, and it has buffer overrun and off by one errors, and this language is responsible for 95% of the security problems in all of computing. It's this programming language, and we teach it to programmers at the beginning. So I'm not trying to say that we should write everything in C. Now, Rust, of course, is a really interesting language that I very rarely like to look at new languages because I think there's nothing new under the sun. But Rust.
So one of my questions? You're hitting all my questions without me even asking.
Sorry.
So
okay,
go on.
Go.
No, go for it. It's brilliant. Go for it. So one of my questions is, should I learn C or should I learn Rust? So carry on. I don't want to interrupt your flow.
And the answer is yes. I believe I'm not 100% sure on that, but I think the answer is yes. But I have to look more closely at Rust. If we can get some memory protection of like a Python language where you can make a string and you don't blow your computer up or create a security hole just by going one beyond the end of that string, then Rust is worth it. And the key thing to Rust is it may not ever be a kernel language, but it's going to be a utility language in Linux. It's been adopted in Linux. And so I think what we'll find, and we saw this in the Mac too, they started thinking about Mac OS tends to like do language du jour, the cool kids language du jour. So you saw for a while, Mac itself was using Ruby to do utility work because Ruby on Rails was all sexy in 2007, 2008, 2009, and now it's not. And then they're like, oh, we're going to go with Python. So Ruby's not the answer. They're going to go to Python. And then they used Python 2. So they started baking Python 2 into Mac OS. And then Python 2 became obsolete and they had to take it all back out. And so this is an example of trying to build utility code in something other than C, right? Like Telnet or Bash or whatever. What would you build Bash in today? And I think that maybe Rust will be that language, right? Ruby was not that language. Python 2 was not that language. I don't think that Mac is now using Python 3. I think that maybe they'll be smart like Linux is and just switch to Rust, because that means if Rust is a long-term commitment of Linux, then it's worth learning. So Rust is the Python of the future, I think. It's a combination of C and Python. But I need to look at it, and it's going to have to evolve a little bit. But the fact that Linux has put it in the kernel, in their next kernel, that doesn't mean we should write everything in Rust. We'll have to see about that, because there are things that, there's affordances in Java that lead to better enterprise software, I think. I think that Rust is a good language for operating system utilities, and we shall see if they start building web servers out of Rust and they start building the next generation of Nginx in Rust and stuff like that. So we'll see. So my goal is to take users back to 1978. That's like in time travel, and read a book that was written in 1978 by people who didn't know the future, right?
And that's the book you've got with you, right?
That's this book. That's the book. This was written in 1978. I'm not sure the authors of this book like this book anymore. Well, one of them's passed away, but I'm not sure that Kernighan still likes this book because it shows him in his sort of youthful honesty and openness and whatever. And so I think that, this book is out of print. I have about 100 used copies of this book. I bought 100 used copies until I found a good one. And then what I did was I digitized the book. And then I had a grad student spend all summer find all the typos in the book. Then I built a website and I made it so that all of the code examples in the book can be run online. And then I recorded the book as a podcast. So I have, and then I also annotated the book. So every time they go in, they kind of break the fourth wall in this book, I put a comment in that says, what they're saying in the previous paragraph is that there was a fundamental change in architectures where we are going from word-oriented architectures to character-oriented architectures. And that's the difference between B and C. Now you'll note that in 1978, they weren't sure which is the right architecture. But then what happens is the future architectures all happened, C happened, Unix happened. In 1984, they wrote this same book and they took all of that innocence out of it, right? They're like, C, great language, you must use. And that's the book that you can have in print because they were confident. They had changed the world between 78 and 84. And we all just bought into this idea. So that's what's beautiful about this book, right? Don't let your viewers all start buying the used copies because then I can't buy them anymore, right? I'm trying to corner the market.
I'm going on to eBay now.
Yeah, corner the market for used copies of this book because they're precious. But because of that, I had to create the book and I made it accessible. The other thing I did when I read the book is I read the code samples. One of the things that's lovely about
Can I just ask you, sorry, you've got that on your website, right?
Yeah, www.ccfree.com, but it's behind a secret code. So if you go to www.ccfree.com and you click on book, it will say you can't see this book unless you can guess the secret code. And then, of course, proceeds to give you many clues about the secret code. The easiest clue to get the secret code is to know the number that I choose for my race car. The secret code to unlock the textbook is the same as the number for my race car. That's all I'm going to say. Or if you've taken any of my other other MOOC classes, it is the number for which, if you ever see it as one of the multiple choice answers, it's always the right answer. So if you got like 4 things and one of them is this number in every class I've ever taught and every test I've ever made, if it's like C and it's that answer, that is the right answer to the question. And that probably for most people watching your show will be way more than enough. They'll get it on the first try, I'm guessing, from that particular description. And that's actually by design. So one of the principles of what I've done is a copyright principle called fair use. And fair use is a way that we teachers take something without asking permission and say, this is historically significant. It's not accessible to blind and low vision users, da-da, 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 da-da. And I'm like, I have no choice but to do what I'm doing to your copyrighted work. And I'm doing it in the name of education and. So what I've done is I've saved this historical moment in ways that the authors are choosing to have it expire. Now, one of the things I'm going to do is I am going to talk at some point to Brian Kernighan. And I'm going to say, Brian, do you love or hate what I'm doing? And I have no way of knowing what he's going to say, because he certainly doesn't seem to show publicly any love for this book. He shows a lot of love for his 1984 book, but maybe enough time has passed that we can celebrate the joy with the joyful voice with which he wrote this book. I talked about C programming for everybody in this book the last time we talked. I have made some progress. I will probably have it on Coursera by June of 2023. I am teaching it on campus at the University of Michigan School of Information to a carefully selected set of 25 students whose main purpose is to figure out if I messed it up. I'm going to teach them. We're going to meet once a week and we're going to look at the book. So it's kind of like a special topics class that really the goal is to fix the course and run through it all and learn C and see if my theories of what's the way to teach it are working well. So I love to teach any scalable class I create. I love to teach it face-to-face. That's an advantage I have that you don't have. I'm also a college professor, right? And so you can make a thing on a Cisco, but you can't then test it with people in the same room who are wonderful students of the University of Michigan who are going to give me a ton of feedback and help me out. And then when I put it up on Coursera, it's usually in pretty good shape. That's the next thing that I'm building. And that will, in June, it will be like the end of a 2-year sprint for me to build C programming for everybody. And then when it's on Coursera, usually for me, it's like done. I mean, it's like I work so much in the beginning to engineer the course that, I can teach 1 million students, one day later, it's ready. It's not like it's got to be cleaned up or beta tested. I beta test all that before I send it out because I only want to do it once. And that will, as soon as I do that, I will immediately start working on the hardware and architecture class. And then after that, I will work on the Java and internship class, Java get to work class. And then I'll be done. Although there's a couple of other things that I'm thinking, I have a saying, it's only my saying, the end of a journey is only the beginning of the next journey, right? When you say, well, I've got it there, I've finished it, it's all done, I've climbed the mountain. Then you go like, wait, dang, now I see that other mountain up there. So I thought this was the mountaintop. So, Rust is actually, we talked about Rust. Rust is actually something I'm thinking about having a little mini short course on. And another thing I'm thinking about is Amazon. And it has to do with what are the core skills that I think every programmer needs. I mean, I think at some point, every programmer needs to know how to deploy something, right? You can't just say, you're going to write code and like your boss is going to take it. So I think DevOps, basic DevOps, and I already got the website, aws4e.com. It just redirects somewhere right now. But I will probably end up teaching an Amazon course. So I was at a conference a couple of weeks back, EDUCAUSE, and I kept running into people from Amazon who are saying, oh, hi, I'm from Amazon. I'm like, what do you do there? Well, I'm part of their higher education engagement team. I'm like, what does that mean? And they're like, well, we just want higher education to just start using Amazon rather than like buying services from third parties that use Amazon. Just how about universities begin to learn to use Amazon, do their own DevOps? And I don't know, do you do Amazon, David?
I use it for like labs and stuff like that, but not like production.
Here's the thing. Amazon is a beautiful, beautiful thing. I run like 35 servers, DevOps. I'm my own DevOps. All my courses, all that stuff, I run them myself. And when they need scaling, I go find a button, I click the scale button. I mean, it's exactly. The Amazon user interface is terrible, but I'm not sure I want them to
I was going to say that.
I'm not sure I want them to fix it because honestly, if you try to apply like user experience concepts to it and try to make it as easy as an ATM, you will actually break it, right? Because the things are in AWS for a reason. And so I think it's more important to teach people how to understand AWS than it is to say, let's make an easy button in AWS. Like, oh, I want AWS, big easy button. Unfortunately, in that easy button is a whole bunch of assumptions. They're completely not appropriate, right? So I kind of love the fact that Amazon is a little clunky. You can get things done. I bet the CLI for Cisco is the same kind of way. It's a bit clunky at times, but you know what? You eventually get things done. I think people just need to be permitted to think that they could do DevOps. And I think that almost all developers need to believe that they can do DevOps. There'll be big places that need to have much more specialized DevOps, but I bet for a bunch of small places, the average developer overlaps with DevOps pretty naturally. So I was talking to people at a conference, and then Amazon, my name started going through the Amazon AI bot, whatever it was. Then my phone starts ringing and hi, I'm your Amazon handler, right? And because I have a company and stuff. And I was starting to talk about this whole education thing and how I want higher education to learn to use Amazon on their own and carry their own water a little bit, because it's just not that hard. And they were like, well, we got a lot of really cool instruction. And I'm like, okay, usually instruction from vendors is terrible. You know that, right? You know,
yep.
that.
Of course. There's a whole industry of people doing training about XYZ vendor. Yep.
Well, the problem if it comes from the vendor is it's really a sales pitch, right? They can't resist selling.
To sell you. Yep. Always.
They go, well, here's AWS. By the way, AWS is the greatest value on earth because of this and this and this. And like, no. I just want to learn how to click the buttons, right?
Exactly.
And so they assured me that their training is great. And so I took their advice and I started looking at their Amazon training, and I signed up for some courses on the Amazon training. The first course is how to get your procurement to approve Amazon purchases. I mean, literally, that's the first course, okay? Now, the second course is what's EC2? What's Aurora Serverless? Really? That's good. Those are the first two things I would teach people. And so the interesting thing is that even though they couldn't resist a sales pitch, they did get some good material. And so the more I look at it, the more I realize it's not really inspirational at all. It's not inspirational at all. They got this whole thing where they tell you that Amazon is a coffee shop. AWS is a coffee shop. And they talk about the doorway, and they talk about the baristas, and auto scaling is like there's too long of a line for coffee, and so you need a new barista. I'm like, huh? How does that help? So should we teach Cisco with a barista model? And then the problem is, they'll start a sentence and talk about coffee, and then they'll end a sentence talking about like the intricacies of auto scaling groups and health checks. I mean, it's like, look, man, if you're so dumb that you have to have such a simple metaphor, by the end of the sentence, you went from like 5 years old to 25 years old in one sentence in terms of the skill, because these people are writing script. I mean, that's just me complaining about overproduced, overthought corporate training stuff, but they have good stuff in it. So,
but you're going to create a course. That's the question,
Yes, I'm going to do what you did, right? I am going to do what teachers really need to do, and that is have symbolic understanding of things, motivate, think about how the learner's actually going to progress, because you're a practitioner, right? Not an instructional designer, right? For you, it's not a script. For you, it's about like, I just got to get this thing in my head out to those students in a way that they can understand it. And then I'll just say, oh yeah, and the textbook for this class is all this other Amazon training, which is pretty good. It's just completely uninspirational. It's just, there's no symbolism to it. There's no connection in it. There's no nothing. It's just a script read by really nice people. And it's not wrong, but they should have just wrote a book.
It's so good to see you saw a problem, eating your own dog food. I think that's the American term, right?
Yes, it is.
You're doing it, and then you seeing the problem with the training, and you're creating a solution for that.
Yeah, I mean, when you're a teacher and a practitioner, right, you understand the value that real teachers bring. Teachers who are teaching from expertise rather than scripts, and passion and belief. I mean, I believe in the idea that schools and universities should directly interact with Amazon. I mean, I just like, it's just in me. And so it's bursting out of me. I can't wait to talk to this very camera and record all these lectures about you are going to love AWS, and you're going to feel so powerful when you use AWS, and not like, it's like a coffee shop.
So the big question is When do we get it? That's the question.
Oh, geez, that's going to be a long time. No, I gotta finish the C class. I gotta finish the hardware class, and I gotta finish the Java
You've
class.
sold us, and now we want to buy it now. Take my
Yeah,
money.
I know. Well, maybe you could do it. Maybe you could teach an Amazon
No.
class.
I'll let you do it. No, that's fantastic. So I want to come back to C because I think there's a list of questions. Like I said, is should I learn C? Should I learn Rust? If I was starting, what would you suggest I do?
Well, I certainly wouldn't start with either C or Rust. Right.
Okay.
I think Python for all perpetuity is the right language. And that's because I just think that to become a confident programmer, you need 6 or 7 programming languages, right? And so it's not like if you can't say that Rust is the best programming language. And so therefore you should start with Rust and go to a Rust boot camp. And 4 weeks later, you're going to be making $200,000 as a Rust programmer. That's just a fallacy, right? That's not really teaching. That's kind of like taking advantage of, you have a little boot camp that's next door to a really big company that needs Rust programmers. And you're just kind of like preparing Rust programmers, manufacturing them and sticking them in the doorway of this company. But that's not a career, right? If that company goes away, this like boot camp was useless. And your next job, you have no idea what to do. And so, you should learn Python. I think people should learn PHP. I think people should learn JavaScript. And so the question is not what's the first language. The question is, what are the superset of all languages you should eventually learn? So, it's Python. I like PHP because, and I like SQL. And then I'm going to teach C. And then I'm going to teach assembly. Then I'm going to teach Java. And there's a difference between that and what you do in the professional world, right? What I'm really doing in that training is I'm getting to the point where you can have a job in a Java shop, meaning that you can do your first internship in a Java shop. That doesn't mean that you shouldn't later learn Scala or something else because you're going to work at a place that does Scala. But my education for you is not so that you can immediately start typing on the job. My education is so that you can learn on the job, right? And so once you've got all those languages, then you can learn other languages and you really don't care anymore what the language is. So I want you to learn so many languages while you're being trained that the next language you learn will be completely no big deal. And one of the things about the C class, and it's really cool because I'm teaching it on campus now, the last part of the C class, which is a kind of a circle back, is not C. It's how did Python build the dictionary object in C. So you take a procedural language with all of its flaws and memory allocation problems and potential security holes, and you build an object-oriented environment. So you could think of it as like how you can go from C to C++. How did C++ get implemented in C? How did Python get implemented in C? And the last of this C class is you are going to build a dictionary object. And the test is I'm going to call your dictionary object and I'm going to stick things in and I'm going to ask for them out and I'm going to ask you to sort them and do stuff like that, right?
That's
and so
nice.
We talked before, the essence of programming is understanding object orientation in context, not just understanding object orientation like I know what this parenthesis does or what this arrow operator does or what the dot operator does, but like problem solving, real problems, large complex code, object oriented. And that's why the end of this C class is going to be implementing object oriented, not so that you can then write Python yourself, but then from that moment forward, the next time you use Python to make a dictionary and add an item to it, in your brain, I know what's going on here. And I know why self matters in a Python object. And I know why this matters in a Java object. And so what is this and what is self? It's some of the hardest concepts in object-oriented programming is why is self so important? I tell my students over and over about what it is, and I know it took me so long to understand that. It took me so long to really understand object-oriented programming. And so I just say it over and over and over again. And by making them build an object-oriented runtime in C, I hope that I'm going to sort of take them down the path where maybe, okay, this is really easy. Because once you know it, it's like, of course, why didn't I think of that, right? I'm glad someone else thought of it before me, and I just can use this stuff in languages like Python and Java.
Should companies be writing code in C, or should they use Rust or something else? Because like you said in the beginning, there's a lot of vulnerabilities using C.
I can't imagine anyone writing C code unless it was like a bootloader or something that was so highly constrained, or perhaps you're in a washing machine and you have so little memory, or you have a processor that's so slow that you got to worry about every single thing. But even then, if you're in these highly constrained, high consequence environments, because if you're writing software for a washing machine, you have no way of upgrading the software in the washing machine. And so your washing machine is simple software, but it's got to work perfectly forever, or you throw a whole washing machine away, right? And so this is where you start in these highly constrained, non-upgradable environments. You might find that C++ is a better language, right? And I'm not sure that you want to put Rust in a washing machine. if you got 4K of memory or something like that. Now, maybe washing machines have 50 gig of RAM in them. I don't think so, but they probably have a little tiny chip that's got 64K of RAM in it and a CPU and nothing else. And it's just 18 cents or something like that. And in something like that, you might want to program C. You might have to program C. And it would be fine at that point, because the need to review your code and test your code and think through everything in your code, it's not so bad when you're just making a control panel for a washing machine. But again, I think that the sweet spot for Rust is going to be utilities, right? A future person might write a Python-like language in Rust, right? Or a web browser in Rust, rather than a web browser in C. And again, I have to evaluate Rust more, but if it's everything I'm imagining, then yeah, we shouldn't be writing web servers in C anymore, or C++. We should be writing those in Rust. And the key thing will be is if Rust evolves to the point that we get memory safety from Rust without having much of a garbage collection cost, then maybe Rust could be used for things like web servers and Nginx, and all those things will slowly but surely be rewritten in Rust. And TCP/IP stacks could be written in Rust. I do think the world has experimented enough with other programming languages, and we do have, in general purpose computing, enough memory to tolerate a kind of a lightweight garbage collection. And so I don't know if you follow Java or not, but garbage collection has been the historical bugaboo for Java forever and ever and ever. It's both the greatest and scariest feature of Java at the exact same time. And interestingly, going back to C, they talk about garbage collection in 1978 as one of the hardest problems to solve, and why it is that they left it out of the language, right? They said memory management is one of the hardest problems to solve, so there is no memory management in C. We put it in a library, and what they couldn't have known in 1978 is how good the garbage collection has gotten. Right. So I've been doing Java since 2002, and garbage collection has been scary. And the Java garbage collection has just gotten better and better and better. I mean, it's kind of like relational databases. Java garbage collection and the join in a relational database are both things that so much computer science brain power has been focused on, and it's yielded. I mean, relational stuff yielded some time ago, but if you go back to 2 years ago, 3 years ago, and you look at the garbage collection aspects of Java compared to the modern Java, the garbage collection is amazing. And so that suggests to me, I can't prove this yet, but it suggests to me that because Java has cracked the garbage collection problem, it means that Rust will steal all of that innovation. And to some degree, Rust was not going to be successful until Java was successful with garbage collection. So we could figure out how to make a fast garbage collector that didn't pause. I mean, the problem, the old Java garbage collector is you're sitting there doing, 100 transactions a second in a web server, and then all of a sudden it's got to do garbage collection. It goes 1001, 1002, 1003, 1004. Oh, back to 100 transactions a second. And that's garbage collection in 2005 Java, right? It's it runs great, it runs great, and then it stops for 3 seconds, and then it runs great again. And then 10 minutes later, it stops for 3 seconds, which you just that is not a good way to run things. It doesn't do that anymore, right? And so the struggle of understanding garbage collection is the reason that we haven't built high performance application in garbage collected languages. So if Rust keeps garbage collection in a little corner over here and uses the latest and greatest garbage collection techniques, then we can write a lot in Rust and it will be awesome. You can't have Nginx pause for a few seconds to garbage collect. You can't do that. You can't have a TCP/IP stack pause for 3 seconds. You just can't do that. You can't have Linux pause for 3 seconds. You can have Twitter pause for 3 seconds, especially if it's got a bunch of servers and it's only one server that's pausing at any given minute, and it routes things around during those 3 seconds or whatever. I mean, Google uses Java for lots and lots of things. So part of the reason that I love this 1978 edition of the Kernighan and Ritchie book is that 1978 is the single most pivotal moment in all of computer science history. And the key thing is you can draw a line. And after 1978, literally nothing before 1978 was true, right? I mean, there was a truth before 1978. And then after 1978, there was a new truth, right? The things that were true pre-78 were not true post-78. Let me give you a couple of examples of that. Pre-78, we tended to write Fortran on computers that were word-oriented. And so they were tended to think about floating point and integer calculations for weather simulations and stuff, because we tended to use computers to compute. We didn't use computers to communicate or write word processing documents or whatever. And so the architecture of computers was tuned to computation, to numeric computation. And so the programming languages were tuned to numeric computation. The hardware was tuned to numeric computation. The problems that we solve were tended to be numeric computation before 1978. And what's happening in the 70s is partly driven by the growth of the ARPANET and the internet, is computers were becoming human mediators for human communication, so that you and I are talking, but computers are mediating our conversation. First, it was mostly text, right? And so what happened is this notion that a computer word had to be long so that you could have high accuracy computations, but characters are short. And so when I was young, you had 10 characters per word, and you would mask and shift to get a character out, right? And when I started, there was no lowercase on computers. We only had uppercase on computers. We wrote code in Fortran. It was like the Hulk shouting, right? And what was happening in 1978, and the thing that C and Unix at AT&T Bell Labs, was these smaller computers were not really aimed at computation. And think about AT&T, it was a telephone company. So it's thinking about communication, not computation. So it wasn't doing ballistics or weather computations or supercomputer simulations. It was just like getting phone calls to go back and forth and getting billing to work. And what is billing? Billing is text, right? It like, oh, you made a long distance call and let's send a bill out later. And so the idea of billing and all that stuff moves from computation as the essential purpose of computers to mediated human interaction. Right? So that you're just getting a bill from a computer, right? Or doing accounting or doing inventory. None of that is computationally intensive. And so what happened is the computer architecture changed from these long words for high accuracy mathematical calculations to single characters, 8 bits, 6 bits, 9 bits, 10 bits, whatever it was, so that you could do characters, right? 8 bits could do upper and lower case from a kind of a Western character set, a Western Latin character set. And then, 1978, that was kind of what mattered, was 8 characters, 8-bit bytes. And so the problem none of the programming languages were suitable. None of the operating systems were suitable. Nothing was suitable. And here you have AT&T moving from a mathematical computation to textual computation. And they were building everything in 1960s, 70s. And there's a language that comes before C called B. And the difference between B and C is B is a word-oriented language that looks like C, and C is a character-oriented language that looks like C. And that's like, whoa, that changed everything. But then what happens, right, is these character-oriented computers were slow and cheap compared to the big supercomputers that were $4, $8, $10 million for one computer, right? These things are like, $100,000, cheap little $100,000 computers that you can throw around. A department could own one or a bank could own one, but they didn't have any operating systems. They didn't have any programming languages. And the problem with them is in the 1970s, these little computers were coming out like pell-mell. They were just like, boom, boom, here's another one, here's another one. And this one's completely different because they were exploring a new fundamental change in architecture of a byte-oriented architecture rather than a word-oriented architecture. And so the problem that they had to solve at AT&T Bell Labs was, whoa, we just wrote an operating system for this particular PDP 8, but now we just bought a bunch of these other things. Crap. Now what do we do? Well, maybe we should just make an operating system and a language that abstracts away the low-level bits of it and just make a compiler for this new thing. An Interdata shows up, a VAC shows up, a PDP-8 shows up. And they had a whole range of new cool computers and old crappy computers, and they wanted to use them all to do things, right? The old hand-me-down computers they would use for email and stuff like that. So they wanted to write an operating system that would work all the way from the latest cool computer they bought to the old crappy hand-me-downs. So they were studying language and operating system portability. And their goal was to take Unix and reduce the amount of assembly language into it to a smaller and smaller fraction. And that was the research. The research was all operating systems were written in assembly language before Unix. And now we're writing an operating system crazy in a high-level language. And then we still have to write a little tiny bit of assembly language. And we have to write a compiler. But that compiler can generate code that's probably faster than hand-built assembly language. And so they're just like, we got all these problems to solve. And so what happened is by the time they were done, and in 78, you see them talking in the book about the Interdata and the PDP and how and we did this in the PDP, and then we had to change Linux and I would change Unix and we had to change C so that it would work with the Interdata. And in that portability, in that sort of progress of hardware progress marching on, they figured out when they got a new piece of hardware, how to quickly get to the point where they had an operating system quickly get to the point where they had a compiler, quickly get to the point where they had some networking, and they could plug that system in, and it was materially the same as all the other systems that they had purchased for the last 5 or 6 years. What this allowed for was it allowed for separately procuring the operating system and the hardware, which meant that if there's a little company that came up with an innovation that was a computer hardware innovation, they could buy that. They could say, you know what, we've been buying these PDP 8s for a long time, but this Interdata company, man, they're cheaper, they're faster, they got more memory. Let's just recompile everything and use this Interdata stuff because that's cheap, because they talk a lot about Interdata, a company that I don't think even exists anymore, in 1978. And so their research was how to use a wide variety of new to old hardware to do the same thing. And then what happened is because they had solved the problem of software portability, hardware vendors could begin to accelerate their iteration time. They could say, and even the same hardware vendor could come up with later versions of the same thing and make changes in the architecture once they realize that this instruction slowed the whole computer down. So we're going to take that instruction out. Whoa, in the old days of assembly language, that would break your code. Well, not in C. You just change the compiler not to use that instruction, and then you recompile everything, and then boom, this new twice as fast computer that had I'm just making this up, twice as fast computer that had one instruction removed, you're working. Like the next, a week later, you're up and running on that new hardware. And so it permitted innovations to happen. And that innovation has led to the Moore's Law, the doubling every few years, and all that stuff. And the most recent thing that we see of this is how Apple switched from, this is a little older, from PowerPC as their core hardware architecture to Intel as their core hardware architecture to an ARM-based M1, et cetera, processor. And it wasn't all that hard. And if you kind of know the history of the M1 it's almost like easy. It's like, of course. But of course, because it's using C and it's using portable languages. And of course, so when they switched from Intel, you could see that happening, right? When they switched from Intel to M1, because they were doing it in all their portable stuff and all their iPads, and like they're sneaking these ARM processors. And I knew some Apple people and are like, you might want to keep an eye on the fact that Apple's hiring a lot of hardware people. We're going to build our own processor eventually. And I'm like, I don't think that's going to work. And of course, I was wrong on that particular thing, right? Apple is now optimizing the hardware on every iteration of the M processor, right? They're instrumenting it. They're running, video editing software, everything. They instrument everything. And they go like, we're going to change the architecture like every year, because guess what? We're using C and portable. Everything's portable. We recompile it. And I can add 3 instructions or take away 3 instructions. And it's okay on a year-by-year basis to iterate. But the one that's actually way more interesting way more surprising than the Intel to ARM was the PowerPC to Intel, because that was a very closely held secret. Because if you go back in time, Steve Jobs spent a lot of time marketing how bad Intel was and how much better the PowerPC was. He wasn't lying, but he was being very selective in what he pointed out, because the PowerPC was a better floating point processor than it was an integer processor, right? And the Intel was a better integer processor. So all the marketing until they were Intel was how important floating point was to things like the charcoal filter in Photoshop. Like, watch how fast the charcoal filter in Photoshop works in a Mac versus a Windows. It's 12 times faster. And that's just because it was floating point. The algorithm was using floating point, which was fast on the PowerPC. Now, other than that, the PowerPC is a terrible architecture for a portable computer. It's big, makes a lot of heat, uses up your battery real fast, and it was not nearly as good as Intel on integer calculations, which turn out to be word processing and stuff like that, which is most of what we do. I mean, what part of your day are you running the charcoal filter in Photoshop? Not much on any given day. And so Steve Jobs, I think, had like a 5-year project that was 5 people that was recompiling the Mac operating system and running it on Intel-based hardware for 5 years in a secret lab that only like 10 people knew about. And I mean, I was at the Apple, I think it was 2007 or 2008 when they sort of talked the Intel, and I was sitting in the room when he walked out and said, we're going to use Intel processors. For me, you could have heard a pin drop. I'm like, you've been criticizing these folks all along, and here you have had a secret project to use Intel processors. And so what they did is I walked out of that room with Steve Jobs in front and said, and the Intel guy, they're hugging, Intel's great. Yeah, like 1 week ago, you said they were terrible, and now you say they're great. I walked out of that room with Steve Jobs, and they had opened this big show floor with a bunch of prototype Intel-based Mac OS. Literally, they had in another room, and they just gave you a root account. You walked in, sat down on a prototype Intel-based Mac box, and I immediately logged in, and I'd been doing development on a Intel-based Mac for years, and I started running the stuff that I ran, and it worked first time. This was Rosetta with a simulation mode. It worked first time, and it was twice as fast. The thing I was doing, which was running a Java application, was twice as fast on the Intel-based Mac on the first day, on the first prototype. That's dramatic. But C is why they could do that. C is why they could have an operating system that secretly they're running on Intel for 5 years and selling on PowerPC for 5 years. And then, boom, I walked out of that room. I called my brother-in-law and I said, if you have any money, buy Apple stock right now. And I didn't buy any Apple stock at that point in time, but my brother-in-law did. He had just gotten like an inheritance or something. He literally put it on the day they announced Intel support. He dumped his whole, not hundreds of thousands, but he dumped all this like money he'd inherited. He dumped it into Apple stock the day Steve Jobs announced the Intel. It was literally the best stock market advice I've ever given any human being in all of history. I mean, I've bought stock and usually I'm wrong. Stock. If I give you advice, it might be good, but if I actually take my own advice, then it probably is going to be a disaster because I'm not very good in the stock market. But again, it comes back to 1978 and the things that were set in motion that led to the PowerPC, to the Intel, to the M1, to the M2, to the M3, to the M4, to the M5, because it's all portable and they can iterate on hardware in the same way that they could iterate on software. And that is the thing that sort of drives technology forward. I don't know if do you have an M1 Mac or are you a Mac guy?
Yeah. No, I've got M1 and M2. Yeah.
I think I have an M1. But here's the thing. I don't know if you've done this, but I go teach a lecture. I don't take a power supply to lecture anymore. I literally,
it's amazing.
I would never walk. That power supply was always like within 1 foot of me at any given minute. I now leave it in my office. I have a power supply. I don't even take it to work. I go to work, I give a lecture, I go to lunch, I plug it into the power supply in my office, and then I go do another lecture. And I never take a power supply to work. And that's because the M1 processor, but it's also because portable operating systems made it so that the M1 processor could do what they do. And they've optimized everything in the name of power. And when the Apple people told me they were hiring hardware people, they were like, we are going to optimize an architecture based on power.
It's amazing that. I mean, I'm actually talking to you on Intel, and the difference between Intel and the M1, M2s is astounding.
I don't understand why I'm not hearing your fan then, right? I mean, if we're talking on an Intel, your fan should be turned on.
Exactly. Yeah, I've got nothing on. I've got nothing on except Zoom. That's why.
Okay.
Yeah, I mean, the fan thing is unbelievable. Like the power you've said. I mean, the power. It's exactly that. You can use M1, M2 laptops for so long compared to Intel, and yeah, fan and heat are typically the worst in my experience on Intel.
Yeah, I mean, I wonder going forward the extent to which crypto influenced the M1 and M2, and the extent to which maybe crypto won't influence the M3. And M4 and M5 and M26 or whatever. I do think that if you look at the first M1s that came out, crypto as a workload was one of the things they were thinking about. And I just wonder if they'll figure out that it didn't work out making a laptop that's good for both crypto and really low power, high capability, low power. And so again, Apple can just wake up on a Tuesday morning, look at all the data and say, you know what, we're going to turn down the chip space we're going to give for crypto. And we're going to turn up the chip space we're going to do for video editing. And that'll be called the M2.3 or whatever. And because of portable operating systems and the ability to recompile, they can just play that. And this is part of the reason in the master programmer, computer architecture is important. Right? Because now we can have this conversation about chips and about memory sizes and all this stuff. And if you don't even know what assembly language is, you don't quite understand how the M2 is profoundly different than the Intel processor. And then if you're going to be a professional, you should have some concept, not that you're building hardware, but you should have some concept of the nature of changing hardware and how that changes what you can do, changes how we can save power across the entire world, because all these cloud servers are just sucking power and doing all kinds of terrible things. But if all of a sudden just a simple iteration can cut that power down by a factor of 10, because it can, portable software is what lets us then save so much energy.
That's amazing. So would you say that C changed the world?
Yeah, there's no question that C changed the world. And the strange thing is that not only did C change the world in 1978, but it's still not a programming language you should use, right? So C is the single most important innovation in computer science, hardware, and software architecture. But I still am not suggesting that you program in it, but I am suggesting that you learn it because it teaches you about the nature of computation. You should use the much better tools for the job, like JavaScript or Python or even Java or whatever. Those are way better tools for getting programming done. But there is no better tool to understand programming than C.
Dr. Chuck, I really want to thank you, not just for sharing your knowledge and experience with us through like videos like this and other things you do, but also for making it accessible to everyone through the courses that you've created and this path to master programmer. I want to give you the floor. Is there anything you want to say? Otherwise, we're going to wrap it up.
I guess the only thing I would say is that people who sort of see scarcity as the way to financial success, they're really mistaken. The key is the world is such a large market, and there are so many people, and there are so many ways to become financially successful without hoarding intellectual property. And I think that if there's one lesson in all of this, both the work that you do and the work that I do, it's that hoarding intellectual property just is like, stop doing it, right? There are ways to be successful without hoarding intellectual property.
Dr. Chuck, as always, thanks so much.
Thanks, David.